All right, so today we are going to be continuing to talk about fatigue, and we're going to talk about stress concentration factors, residual stress, and then do an example of uniaxial stress. So just like we saw in the static case, if we have changes in the cross-sectional geometry, that leads to a stress concentration, shows up in things like O-rings, grooves, fillets on shaft diameter changes, and etc., including fasteners and through holes. Every time we have these changes in geometries, you should always look at them and just see them as stress concentrations in places where your component will likely fail. And what we try to do is keep the geometry such that we reduce these stress concentration factors. Okay. When we treated these earlier, we saw that some local yielding was acceptable in ductile materials, but that's not the case for fatigue. Okay. So because under cyclical loading, ductile materials behave like brittle materials, we have to consider the fatigue case as well and adjust the stress concentration factors to account for dynamic loading using the fatigue stress concentration factors. Okay, so we'll talk about how do we do that. So this is just a review. These are all the stress concentration factors from the appendix in your book for different load conditions and different geometry changes so that we can adjust for them. And notice we have equations for these where we can, based upon the change in change in geometry and the radius, we can calculate that. And in general, we want these radii to be larger for these static stress concentration factors. We need to introduce something for fatigue, which is called the notch sensitivity. And that is a measure of a material's sensitivity to stress concentration. And this shows up in fatigue applications. In general, ductile materials have a lower notch sensitivity. The notch sensitivity fortunately decreases to 0 as the notch radius decreases to 0, which is possibly counterintuitive from our static stress understanding. Okay, and we'll show the equations and how that falls out. That's the opposite of the stress concentration factor. Okay, so it's an important point that when you're dealing with fatigue, that you understand that when we deal with fatigue, we have this parameter called notch sensitivity, and it has sort of this inverse relationship with the static stress concentration factor. So we'll start though with that static stress concentration factor and modify it to get our fatigue concentration factor. And the way we modify it is through that notch sensitivity that has sort of that inverse relationship that we might expect with the static stress concentration factor. The effects of the notch sensitivity are more pronounced in the high cycle fatigue region, but we use it conservatively for 10 to the 3 and greater cycles. And this is the equation to calculate our fatigue concentration factor. We have this equation here where we just add 1 plus this notch sensitivity parameter, which we'll show you how to use, times our stress concentration factor from our static analysis minus 1. Q is the ratio here of the fatigue concentration factor minus 1 over the stress concentration factor minus 1. Or we can express the notch sensitivity in terms of 1 over 1 plus the square root of A over square root of R, where A is Nueber's constant in inches, and R is the notch radius, in this case in inches. Okay, and this is what the Nueber constant looks like as a function of the ultimate tensile strength of a material. Okay, so in wrought aluminums that are either heat treated or annealed or strain hardened, we get these curves here. In low alloy steels, if they're loaded in torsion or tension, we get these values here. Okay, so this is what, when we plot that Nueber constant as a function of the ultimate tensile strength for these different materials, this is what we get. Okay, so the Nueber constant also depends on the material and the manufacturing process. Okay, if we use this equation here to calculate the Q, then, and if we plot this as a function of the notch radius and the Nueber constant for that material, we get this graph here. Okay, and notice how we get these different lines, and these different lines are for these different materials that have these different ultimate tensile strengths. Okay, and for steels, we can look up their ultimate tensile strength and then come over here and find the Nueber constant, and then we can go over here and plug in the notch radius to find the notch sensitivity, and then modify our stress concentration factors. Now, what's important here is this relationship. Okay, so this is the opposite of what we have for static stress concentrations. Okay, so if you see that if the notch radius is really small, then our notch sensitivity is small down here. If the notch radius is larger, then we have these higher values here. Okay, for the notch sensitivity. These are notch sensitivities for heat-treated aluminum, annealed and strain-hardened aluminum for those aluminums with these different ultimate tensile strengths. Okay, so we can go here and then pick this Nueber constant and then find our notch sensitivity. Okay, so how do we use it? So this is just an example of how we use it. This is the static stress concentration factor. We have this rectangular stepped bar. It's a rectangular stepped bar. And it's under bending stress. So we use the flexural formula to find the nominal stress. And then we can pick our static stress concentration factor based upon the geometry of this stepped bar. And we want to find what the fatigue stress concentration factor is for those given dimensions. Okay, so here's the dimensions, they're given, and we find that the ultimate tensile strength is 100 kpsi. So we'll start off with the static stress concentration factor. We plug in the values for the geometry, and we find that the static stress concentration factor is 1.56. Okay, so we have 56% more stress at this notch because of this stress concentration factor. So now what we want to do is we want to find out the notch sensitivity of this material so that we can modify the stress concentration factor to find the stress that we should use when doing the fatigue analysis. Okay, so what we can do is just calculate the notch sensitivity here by using the tables to plug in our Nueber constant. We put in the square root of the radius of that notch here. And when we do that, we get 0.89. And then we see that the fatigue stress concentration factor can be found just by plugging in the static stress concentration factor, which we found from here in this table, and the notch sensitivity parameter, which we just calculated here using the Nueber constant for that material. Okay. So doing that, we actually see that we have a fatigue stress concentration factor that's actually slightly lower than our static stress concentration factor. Okay. So that's how we go through that process. And that's obviously not always the case that it's lower. So let's talk about residual stress. Residual stress is the stress that remains in a material that's often due to how it's manufactured. Okay, so when we order metals, the metals went through some process, usually some form of forming and or heat treatment, and those processes will often leave some residual stresses in the part as, a function of the cross-sectional area. Okay, sometimes these are residual tensile stresses, sometimes they're residual compressive stresses, but they're extremely important for us because the residual stress in the surface can dramatically affect the fatigue life. Since fatigue is very sensitive to tensile stress, and it benefits from compressive stress, in other words, fatigue life is improved with that compressive stress, then our compressive residual stresses can improve fatigue life considerably, and tensile stresses can reduce fatigue life considerably. And we can introduce these compressive residual stresses either by thermal treatment, surface treatment, and mechanical pre-stressing, okay, or cold working. Compressive stresses at the surface are often introduced to improve fatigue life. Okay, this is a huge industry surrounding introducing these residual stresses. For example, shop peening is done for a lot of rotating machinery parts, gears, and etc. So if we introduce stress at the surface, though, that stress has to be balanced by some compressive stress inside the material. Okay, so we always have to have our forces balanced, and if we have compressive stresses at the surface, then we're going to have tensile stresses inside the part somewhere. But that's not necessarily something that we are as worried about, because the fatigue failure mechanism starts with cracks at the outer surface, not usually inside the part. Okay, and those outer surfaces are often where the stresses are the greatest. And when we add these compressive stresses at the surface, we can kind of knock down the stresses that are experienced due to loading. Okay. If there is too much internal tensile stress, though, it can also cause failure. Okay, so there's really an art to processing these materials in such a way that you can really stretch their life. That's pretty good. All right. So for residual stress, we find that high yield strength materials benefit the most. Materials that have less than about 80 kpsi show little long-term benefit of residual stress. Residual stress can be introduced through thermal treatments, such as case hardening. Through hardening is where the entire microstructure of the material is changed throughout, versus case hardening where we're changing the properties of the metal out of the outside surfaces. Through hardening is not so good because you make the entire material more brittle, so it's typically not good to do for fatigue. Case hardening, on the other hand, can introduce those compressive stresses just at the surface. There's also other surface treatments that are more mechanical, such as shot peening, and that's where we shoot small media at the surface, and when it hits the surface at high velocity, it locally deforms that surface. There's also laser peening, which has a similar mechanical phenomenon, and then cold forming, where we are cold working the outer surface, and then mechanical prestressing, where we sort of bend something in a certain direction. I'll show you an example of that. Through hardening, which we said is not great for fatigue, it hardens the material, which increases its ultimate tensile strength, which is traditionally good, but it creates residual tensile stresses, which promotes crack growth, and that's not good for fatigue. So it's not really desirable for increased fatigue life. Case hardening, on the other hand, where we harden the outer surface of the material, is wonderful because it can create residual compressive stresses at the surfaces. And this is done by carburizing, nitriding, and flame reduction hardening, where we heat the outer surface in a carbon-rich or nitride-rich environment. And those carbon and nitride elements can enter that material and make carbides and nitrides on the outer surfaces and make it a lot harder. When you're adding those elements, you're creating those compressive stresses because you're having this local diffusion / volume change in the surface and or phase changes in the material in its microstructure, which causes it to produce residual stress. So if we take the outer surface, so this would be like the surface of some component. You can imagine that this is the top of a shaft. And these are the stresses. So this is 0 stress, and this is minus 150 kpsi. This is the curve for a nitrided surface. And what you see here is that when it's nitrided, this top surface has these compressive stresses that are pretty high. As you go into the middle of the part this way, you see that those compressive stresses peak at some location below the surface, and then they drop down and go back to 0. And if you follow them, they actually go back into tensile stresses, because these stresses have to be balanced in the material. If you look at a carburized surface, the carburization is not as dramatic necessarily as the nitrided surface, where we have a little bit lower compressive stresses, but it goes deeper into the material. So those compressive stresses are distributed more deeply into that material as its cross-section. Now, if we look at the top surface and bottom surface, and we follow those stresses down, for example, a carburized material, and we start here at the top surface, after carburization, we see we have these compressive stresses here, these negative stresses, and they go down pretty deep from the top surface. In this case, I'm not 100% sure which dimensions these are. We go to 0 and then 150 and then back to 0. I think these are in inches. So this would be like 50 thousandths. It goes into the surface, which is pretty deep. And then at some point, these stresses have to be balanced. These compressive stresses have to be balanced with tensile stresses. And so we get over here, and inside the material now we have these tensile stresses. Okay, and then we come back and we get these compressive stresses at the surface. Now, because fatigue is a crack initiation, propagation, and then failure mechanism, we really care about these compressive stresses at the surface. Okay, so a lot of elements are called out to be case hardened for this reason, and this is the mechanism that causes it. So shot peening is a mechanical process where you are shooting these Small pieces of material, such as glass, steel, cast iron, walnut shells, and they're shot at the material, they cause deformation due to their high velocity. So you're shooting these elements here at the surface, and you use typically harder shot for harder materials. And the yielded surface material is stretched and then compressed by the inner material. Okay, and that results in a net compressive stress. Okay, and in fact, if you compare the surface peened compressive stresses versus a nitrided surface, for example, you can actually introduce these even higher stresses here. And this is for hardness of 64. That's a rock hardness Rockwell C 64. If you have softer materials, then here that's shown here, this is a softer material. But you can see here as, these different materials with different hardnesses will have a different benefit from shot peening. So in general, your harder materials can benefit more from this, which is good for us because often we want harder materials because they have a higher ultimate tensile strength. And then we can further improve their life through nitriding, carburizing, or shot peening. Cold forming is also used, and that's where we work the metal's outer surface. So we shape the metal below its recrystallization temperature. That means it's not melting, so it kind of stays in that phase. This is used for a lot of small parts, and it's accomplished by in general forming, but we say squeezing, bending, shearing, drawing. It leaves the metal harder because we exceed the yield stress in the stress strain diagram, which causes strain hardening. Okay, so if we do that just to the outer surface, then it results in a net compressive residual stress. Okay, so sometimes this is used if you have holes. They'll undersize them and then come in and cold form them to make them slightly larger. By doing that, they increase the strength, the fatigue strength of the holes. So you'll see it in fillets, grooves, and other stress risers. And this is just an example of a sequential cold work sample into a final shape. Okay, so there will be a lot of residual stress that remains in the part due to this cold working process. All right, so this is an example of mechanical prestressing, which is another way of introducing these residual stresses. Okay, so this is a leaf spring. This is a leaf spring for a vehicle. And so what's done is it is overstressed and then preset. That's the overloading, the mechanical stressing. And you can use this presetting with shot peening to really improve the life. So what's interesting is what we'll walk through here. So this is the untreated leaf spring, and then it goes through these different processes here to try to introduce these residual stresses. And this is the state of stress for each of the processes. Okay, so the first thing you do is you pre-stress above the yield strength, and this is called presetting. Okay, so it'll go up to the yield strength and then start to deform. So these are the yield strength and compression. This is the yield strength and tension. These are even, so this would be an even material. So you come down here and you bend it. And when you bend it, you have these tensile stresses at the top surface and these compressive stresses at the bottom surface. So you come up here, but when you get yielding, you get that deformation. So it kind of clips it here. Okay, so we have a tensile stress now at the top surface, and we have a compressive stress at the bottom surface. When we let it go and relax it, And we have this state of stress where we now have these compressive stresses at the surface, these tensile stresses at this surface, and then compressive stresses below the surface, and then some tensile stress here, which is undesirable at the bottom surface. Okay, so then what's done is the top surface is shot peened. And by shot peening, these compressive residual stresses are introduced, like we saw. Okay, so we have these compressive residual stresses in there, and then when we put it in service, the service direction is actually opposite for this bottom surface. So that what we end up with is these much lower stresses at the surface here. Okay. And then we have these compressive stresses, which we actually like to have below the surface. So it's a pretty fascinating process for improving the life of these components. And these leaf springs can last forever, but they don't last forever just because you took some metal and bent it in. There's some pretty clever people that actually went through these processes, so that at the end of the day we have these desirable stresses at the surface. So this is just an example of some of the options that you have to improve fatigue life. Okay. So now we're going to talk about how do we design for high cycle fatigue. So if we have something that we're designing and we expect it to be in service for a large number of cycles, and this is often the case for rotating shafts, for example, then we have essentially 4 different categories. And the Norton book delineates from some of the other books because they treat different categories in different ways. But because we calculate the von Mises effective stress, we actually account for the other conditions. And so the more, I would say, both academic and the more scientific and pragmatic approach is to just calculate the von Mises stresses. When we do that, it accounts for each different case automatically, including bending, axial, and torsional loading. Okay, so we have these different categories of stresses that our material might experience in a fatigue stress. And the fully reversed stress is where we have a mean stress of 0. A fluctuating stress, as we saw last time, is where our mean stress is not 0. So if we have a fully reversed stress with under uniaxial stress, it just means we have one loading direction, if you would. And this is category 1. We'll talk about that today. We also have these categories 2, 3, and 4 stresses, which are a little bit more complex, and we'll have to deal with them a little bit differently for our safety factors. Okay, so we have fully reversed stress or fluctuating stress. That has to do with the mean stress. So either the mean stress is 0 or the mean stress is not 0. These rows have to do with whether we have like a uniaxial stress or if we have a multiaxial state of stress. And we can calculate all these stresses directly from our von Mises effective stress and then use those in the analysis. Okay. So these are the steps. They're going to be the same for the other categories. And I'm putting them here. My intent is to have all the content sort of in one place that if you can understand the lecture and you can understand the slides, then I am hoping to save you a little bit of time than having to go back through everything. And if you can follow what we do in the lecture, then you can use the textbook as a resource. But in this case, the design steps are worth going through for these fully reversed stresses. Okay, so we'll just talk about these. This should be mostly intuitive by now, but of course where we want to start is how many cycles do we expect that component's going to have? How many years do we want it to run? Is it going to be the failure mechanism? Is something else going to fail first? What is your warranty period? What will happen if it breaks? There's a lot of things that are part of the design requirements that'll kind of influence, how many cycles of loading we're going to experience. And then we just look at the loading. Okay, we look at the amplitude of the applied alternating loads from the zero to the peak. Now in this case, we're saying this is where our mean stress is 0. So we're just considering the alternating loads. And if we have a different category, we have a slightly different process. And this is where it can get a little bit, this is where we just need to have enough time to make sure we go through the process, okay? Because we have to kind of design a geometry to see what the loads are. And then we have to look at the loads and see if they're going to cause it to fail, and which may cause us to go back and design the geometry. So there's this native chicken and egg problem for so many of our design problems, where we have to kind of do something. And it's really why I'm pushing EES, because it's nonlinear system of equation solver. So you can really put all your equations in there. You can put all this information, and then you can play around with the variables. And all of the other variables are automatically accounted for, and it's easy to solve. So we may from experience know what this geometry is supposed to look like, but let's say we know how many cycles it'll experience. We kind of know the loads that are going to be put in there, and then we pick the geometry so we can calculate the stresses. And then we need to make sure if we have any stress concentrations factors, either for axial bending or shear loads. We have to look at those for those parts geometries. And then, of course, we try to pick geometries that don't cause unnecessarily high stresses. And then if we haven't already, or if we don't have a requirement for a material, we have to pick a material. Okay, so we'll have to pick a material based upon kind of what we need in terms of its tensile strength, yield strength, endurance limit, or fatigue strength if it's a wrought material like aluminum, and then its notch sensitivity. And we basically kind of put all this stuff together or do estimates. And this is really the magic of engineering here. It's going from sort of these requirements into that embodied design. Okay, and then we correct our stress concentration factors for our fatigue concentration using the material's notch sensitivity and the Nueber constant for that material, which we just talked about today. Okay, so then what we do is we calculate the nominal stresses. Okay, at those critical loading conditions where we expect the stresses to be the highest. And then we correct them if necessary with the fatigue stress concentration factors like we just talked about. Okay, so after we have the geometry, we have our concentration factors for the material, we pick the material, then we calculate our principal stress amplitudes for the critical locations. Okay, and we need to make sure that those principal stresses are the stresses that include these stress concentration factors, and then and only then do we calculate the von Mises effective stress. Okay, so then at that point we go through our correction factors, which we talked about in the last lecture, where we correct for the part size, the load, the temperature, and all 5 of those factors. After we pick all the load factors and based upon the temperature, the environment, the load, etc., then we have a corrected fatigue strength, and we have the number of cycles. Okay, so then we can create our SN diagram, our fatigue strength life diagram, like we showed in the last lecture for that material choice. Okay, so once we have that, then we will compare the alternating effective stress at the most highly stressed location with the corrected fatigue strength. at the number of cycles, and then we make sure that the safety factor, that stress that it's going to experience, the ratio of the corrected fatigue strength at that number of cycles that we have to design for over the von Mises effective stress, is such that we are, below, what we need to be. So we have a safety factor that, is at least 1. Okay. And we have the guidelines from the beginning of the semester that tell us how to choose safety factors for different applications. Okay. Now keep in mind that if you introduced in your corrected fatigue strength calculations a reliability of 99.9%, for example, you're already increasing the safety a little bit. And then here, this is sort of our last step where we can add another little bit of margin of safety. Okay. So, in this point, it basically says, now we get all the way to this point and we don't know if it's going to survive or not. Okay. So if the material doesn't work, then we have to go back and redesign it. So usually if you kind of know the material and you have the number of cycles and you can't really do much about the geometries and steps, what you can do is maybe change the geometry a little bit, make it a little bit larger, reduce the stresses, and then, or if that doesn't work, then you can change the material. Okay. Or you can go back and maybe even say, well, maybe we don't really need it to last that long because it's going to be too expensive for us to go this route. And we'll just put a warranty on there that has less time. And, if it lasts for 5 years, our customers are going to be happy anyway, blah, blah, blah. Okay. So there's a lot of design that kind of goes in here. And what your responsibility really is as the designer is to make sure that you're following this correct process. Okay. So hopefully this makes sense. So let's just go through this with an example. Okay. So this problem here is design of cantilever bracket for fully reversed bending. Okay. So this is something that we might experience if we had a bearing on here, and something was rotating under load, because this would be similar to like half the Moore machine, or in this case, we just have this load that goes back and forth in, between positive and negative values. Okay, so we're told that the max load is 500 pounds, the minimum is minus 500 pounds, and we need to design a bracket to support fully reversed bending for 10 to the 9 cycles with no failure. So we're looking here, we see that we automatically want to go to a steel that has an endurance limit. And we have this additional requirement that the dynamic deflection cannot exceed 0.010 of an inch. We're told that it's in air. Okay, so our temp factor is going to be 1 because it's below 450 degrees Fahrenheit. The maximum cantilever length can be 6 inches, and we only need 10 of these. So, how are we going to make them? Okay. So we're saying, okay, well, we can fix it here where we have this bolt that goes through the beam, it's creating a cantilever. They say we can ignore this stress concentration here. And they say it would be nice to be able to machine these because they only need 10 of them. Okay. So this is a pretty typical design problem because where we know the loads, but we really don't know the geometry. So our job is then to, just pick something that's going to survive those loads and won't fail. Okay. So we have to do the static analysis, find our loads. Okay. And in this case, for this material, because we only need 10, we get a stock material that's just slightly oversized, and then we can machine it, turn it down, so we get the near net length. Okay, in this case, a piece of cold rolled bar stock from the mill would be cut to length, drilled for the holes, and then it would be machined to give us that outer surfaces. So then we know that what that surface finish is likely going to be. Okay, and it's saying here that, you know, if we're going to put a load here, we don't know what the mill tolerance is. So if we just bought this material from the mill, it's not necessarily going to come in with the high enough precision or geometry, so it'll have to be ground or turned. Okay, so this geometry here we have to consider. So this is the simplistic design. This introduces a stress concentration factor of about 2. If instead we get a slightly larger size stock material and then machine a larger radius here, then we can drop that stress to about 1.1 to 1.5, depending on the geometry. Okay. So right off the bat, we can kind of start to use these design principles to minimize those stresses. Okay. So then we have to pick some dimensions. Okay. So in this case, some dimensions are picked, they're guessed. And then we have to pick material. In this case, a low carbon steel is used that has 80,000 psi because this is cheap, it's readily available, it has an endurance limit, and so we just pick that material to see how it'll work. And then we go to analyze the forces. Okay, and notice, you know, we needed to kind of get our stress concentration, so we had to define some geometry first before we go in and calculate all the forces, because, you know, after we calculate them, we're going to have to adjust them for these stress concentrations, right? So here we just do static load analysis. The reaction force is equal to the applied force. The applied force at the distance provides us with a moment, which we can calculate here. We can calculate the moment of inertia and the distance to the outer surface of this beam, so that we can use the flexure formula here, MC over I, to get our nominal amplitude of oscillating stress. Okay, this stress is due to bending, right? So this is our bending stress in that material, and it's 26,667 psi, which is a little under half of the ultimate tensile strength for that material. Okay, so then what we need to do is calculate those ratios for the stress concentration factors, so we can go to the graph for that loading condition and get our stress concentration. And we can kind of already tell that, you know, we're a little close to, you know, just with this value and this value, you know, we may be a little bit too close to the yield stress for that material. But let's go through the process anyway. Okay. So if we do that, we get our static stress concentration factor for that particular geometry that we chose. And we get it that it's 1.29. And then we'll, since it's in fatigue, we'll get the notch sensitivity. Okay, so we get the data for the Nueber's constant for that material from table 6.6 in the book. We're told that ultimate tensile strength is 80 kpsi, and the square root of A is 0.08. So we can plug those values in and get a Nueber constant of 0.862. Okay, so then what we can do is get the calculated fatigue stress concentration factors. Okay, and in this case, it's larger. Okay, it's larger than it's larger than 1, but it's less than KT. So we use KT here for the static case to make sure that we don't have static failure, and then in this case we're calculating KF to make sure that we don't have a fatigue problem either. Okay, so then we can calculate our alternating stress for those cycles, and in this case it is 33,343 psi. And then using this stress, we can calculate our principal shear stress from these equations here that we get from our calculating our principal shear and normal stresses. And we find that the principal stress here, 16,672 psi. Okay, so now we have our two principal stresses that we can calculate from our Morse circle. Okay, and then we calculate that it's 33,343, which we would expect, okay, because we have this on the normal direction, the principal direction. So then we can calculate our von Mises effective stress, which is also what we would expect, the same stress. Now, it's good practice to go through this, okay, to use these equations and make sure that we don't have any stresses that we haven't accounted for, okay, even if we know that we're going to get the same answer. All right, so then the next thing we need to do is find our endurance limit for that material. And as we saw, we can start off with 50% of the ultimate tensile strength as an estimate for the endurance limit, and then we have to correct it. We can calculate our A95 area and equivalent diameter, and then calculate our size factor, okay, and it's 0.9 for this case. Okay, so we've automatically reduced the fatigue strength endurance limit by 10%. Then we can get the rest of them. The load factor is 1 for bending. We want a 99.9% reliability. So that gives us a reliability factor of 7.753. We're told it's at room temperature. Okay, so that's 1, and we're told that we're going to machine it, which tells us something about the surface. So then we plug the values in for the machined part from that relevant graph for that material, and we can find that we have a surface factor of 0.85. So we put all these together, and we find that the endurance limit here, okay, if we want to have an infinite life, we have this corrected endurance limit here, which came from our 50% starting point for the endurance limit, and then we go through the correction factors, and we find when we multiply this all out that we have 22,907. Well, it's obviously a problem, right? Because we found that our stresses are here, so we're not going to get infinite life with this design. So at this point, you may be frustrated, and because you have to go back and figure out how to modify your design to hit that limit. But this is normal, so just embrace the process. Okay. So if we take this and we can calculate the safety factor and the beam deflection, okay, because we were also given this requirement here at the beginning that its dynamic deflection cannot exceed 0.01. Okay, so if we're experiencing the stresses, we can plug in that beam equation using our singularity functions, which you can find in the appendix of the book. Put in the deflection at x equals a, and we find we're at 0.026 inches. Okay, we're allowed 0.01. So the design fails for both reasons. We have excessive stress where our safety factor is less than 1, and we have excessive deflection, so we have to have more material or different material. Now, the easiest thing to do is probably add more material. Okay, so the first design, this is the first iteration here where all these values are calculated. The deflection is too large, the stress is too high. Okay, so we have to iterate. So since the dimensions can be changed and the material can be changed, we kind of have those 2 degrees of freedom. Okay, so either we can find a harder material with a higher SUT, or we can change the geometry to make it a little bit larger for this application. So in this case, the material for the second iteration, in this example, the material was left unchanged maybe because of cost reasons, because it costs about the same if you get a little bit larger material and you're going to go through the same machining processes. But the beam cross-sectional dimensions and the notch radius were increased. Okay, so you can change these parameters when you have everything set up parametrically, like in the EES. You can just play around with these and look at everything and it'll all fall out. And you can play with your design. So the final dimensions were chosen such that B was 2 inches. So B is the width. It was chosen to be 2 inches. D was 1 inch. Big D was 1 and an 1/8 inch, and the radius was 0.5. And the rest of these parameters were selected. So it drops the fatigue safety factor a little bit, and it adds more material for the stress. So when you go through when they went through the redesign, you can see how these parameters changed: B from 1 to 2, 0.75 to 1, 0.94 to 1.25, 0.25 to 0.5, etc. Okay, so if you go all the way down here, the endurance limit is, it's almost the same. The corrected endurance limit is almost the same, but because we have more material, we have less stress, and the safety factor jumps up to 2.5, and the deflection jumps down to 0.005, which is 5 thousandths, which is below the required 10 thousandths that we saw here. Okay. So this is a fantastic example. This is an example that you should read through. This is an example that you should work. This is an example that you should probably plug into EES and play around with the design parameters and understand. Okay. And also there's this reminder I placed here that, even though we did the von Mises stress and we knew that the principal stress was going to be the von Mises stress, and it's redundant, it's still very important to set up the equations to make sure that we don't miss anything for our stress calculations. So this is a very complete mechanical design, process to design for fatigue. Okay. So we'll talk more about this next time. So we'll stop here and we will pick it up in our next lecture and talk about how do we calculate the safety factors for these designs when we have this alternating stress and mean stress.